Hello there. This is John Straub, and I'm just going to give you a quick, short video that tries to expand on the difference between the building enclosure and the building structure, in particular when we talk about the support function. So if we recall, when one breaks down the building into reasonable small number of systems and categories, you end up with the building superstructures or substructure, which together are the building structure. Then you have the services like lighting, HVAC, plumbing, and all the rest. You have the fabric, which is the interior subdividers that are another of those things, suspended ceilings, partition walls, built-in furniture. And then we have the enclosure. Now, of course, the enclosure is often understood to be the component of the building that separates the outdoor environment from the indoor environment. Part of the three categories of functions that the enclosure fulfills is that of support. And the word support was chosen to identify the structure-like behavior, meaning it resists mechanical loads like its own weight and wind loads. But it's not the same as the superstructure because often those are two completely separate things. So to be clear, the superstructure or structure is going to be the things that we would recognize as columns, slabs, elevator cores, bracing, and so on. And they're not even really the physical component because what they are is they are part of the components of the building that transfer loads. So what we mean by that is that they collect and transfer gravity loads and lateral loads primarily. That means all the weight of the building, all the weight of the occupants, all the forces caused by occupancy, snow loads, etc. And we define the structure as being those components that are connected together, have appropriate stiffness and strength to take those loads and deliver them to the ground. And I'm saying the designers are making that choice. Not all, let's say, columns are part of the structure. The column might be just there to hold a light or something like that, which makes it part of the fabric. So it's a decision and an actuality of how it's constructed, whether or not it's part of the building structure or not. So we're going to start with the building structure, and then I'm going to differentiate the building enclosure, and we're going to go down some of the big picture technology choices we have available. So to start with, we have the building structure. Although it seems like you have a huge number of choices, really we have four materials that are commonly used to make up the building structure. And then we have the form that we shape these materials into to create a structural system. Now, I start with materials because when people are early coming to building structure and lay people, they routinely describe the structural based on its materiality, which is actually not correct. Meaning, it's not that it's wrong to describe the materials used, it is that the primary important feature of a building structure is its form, not its material. But let's just take a look at those materials. We often call it concrete, where we usually mean reinforced concrete. We talk about steel. Usually we mean hot rolled steel, although, technically speaking, you could have cold form steel. We will talk about a wood structure. Much of what is actually built as wood structures are light framing, but closely spaced, smaller elements. But that said, we're seeing a lot of more interest in mass timbers, and we have a long history of post and beam and log buildings. And then we have masonry, which is very common outside of North America, where that material called masonry is, usually made of some sort of mineral-based adobe or brick or stone. And in the modern world, almost all of it is some form of concrete or calcium silicate. But as I said, it is not the materiality that actually is the most important decision. It is the form that we shape. And again, there's not as many choices at a big level of how we form our materials to form a structural system. The one obvious one is to make it out of walls and floor slabs. You know, you can do solid floors, solid walls, put them together, you have a structural system. Now, by solid walls, we're often dealing with what we would describe in the profession as shear walls, because they're really good at taking lateral loads in shear down to ground. But of course, a solid shear wall made of, say, 8 inches of reinforced concrete can take an awful lot of vertical load, and hence it's used for gravity loads as well. Now, when I call them solid walls, I'm doing air quotes around that because we also have a lot of small or medium-sized holes that form in a solid wall, which don't weaken it that much. And so it's still a solid wall, shear wall structure. The use of closely spaced members like wood studs or light gauge steel studs, when combined with some sort of structural sheathing or bracing, form the equivalent of a wall. So they're not nearly as strong, but they behave in very much the same way as if it were a concrete wall or a masonry wall. It's just that they are much more lightweight and weaker. The other big category would be framed systems, where we have both frames that are braced to deal with lateral loads, or use moment connections between beams and the columns to form the lateral resistance aspect. And so that's really like 4 categories there, right? There's a few other ones like tension structures, inflatable buildings, arches, domes, but these are pretty rare. It's not that they're unimportant and uninteresting. In fact, they're very interesting. It's just that we don't use them a lot because they have lots of limitations about how we can use them. So when it comes to the actual selection and understanding of what is going on in a building, what's the superstructure, we're combining these 4 types of materials with these 4 types of forms or systems to make roughly 16 combinations. And actually, some of these combinations are just not used in the building industry, such as solid, like steel as a material, and shear wall are rare. They're occasionally used, but mostly they're used in places like ships. The most common superstructures that we see in the buildings today would be hot rolled steel with braced frames, reinforced concrete as a moment frame, reinforced concrete as a shear wall. Those are both very common, and solid masonry used as a shear wall as well. Those would be the 95% plus of the superstructure systems that we see today in the building industry. Now, we have to keep in mind, before I go on and show you some examples of building structure, that there are definitely important examples where the superstructure and the enclosure support are combined together. The most obvious being light wood framing sheathed with OSB used to make 1 to 3 story buildings. I mean, they're all over the place. So that is why it's worth identifying that superstructure is often a separate thing, especially in larger buildings and commercial buildings, but sometimes it's together, and it's our job to understand, both in design and analysis, why are they separate, and why are they separate, and when should I make them separate. So here's some examples of shear walls on the left there, upper left. Moving around to the upper middle, we have a braced hot rolled steel frame, very common in light industrial. Then we have on the upper right, we have the plywood sheathed over top of light wood framing to make it essentially a wall that's got holes in it. In the bottom left, you see a commercial high-rise version of that. This is a complete concrete wall with modest size openings in it that don't limit its strength as a shear wall too much. The bottom middle is a moment frame, our own Engineering 7 building. And you can see that's quite a common system as well for low and mid-rise institutional commercial buildings. And on the bottom right, we have some sort of a light framing with bracing, which is less and less common as we discover that it's hard to get an appropriate amount of lateral bracing out of it. So the moment frame, if we dig in a little bit, is almost always designed out of concrete, although in some special applications in the building and also some special buildings, especially seismic zones, we might choose to use moment connections. Moment connections between slabs and columns, beams and columns, are relatively inexpensive when made out of reinforced concrete and quite expensive when made out of steel. It's not a technical problem. It's a trade and dollar problem. Again, here's an image from E7. Pretty clear that you can see the reinforced concrete. There are no braces. There are instead thickened connections to the slabs. Also, it's worth noting all those steel studs inside. That's all fabric. That's just going to be partitions that can be moved around at a later time. Now, frames and shear walls are widely used, and those frames can be made out of a number of materials, as we've described. And the idea behind a shear wall being that it transfers those lateral loads by shear primarily. The moment frame transfers those lateral loads by bending moments, which then impose bending moments in the columns, which then also take the force down by shear as well. And then we have braced frames where the lateral loads are transferred and converted into tension forces, a little bit of compression forces. That's the most structurally efficient solution, and hence often the lowest cost solution. So that braced frame approach is what is used in so many lower rise buildings, and widely used in steel, to a lesser extent wood, although we're seeing it more often in mass timber. So this is a photograph of what that might look like. This is a one-story strip mall under construction. You can see the red hot rolled steel and the columns and the beams, and there's pretty clear X-bracing in here to transfer lateral loads into tension and direct them direct to the foundations. Now, frames are often desirable because they allow much more flexibility in where you put your openings in the building enclosure. So if the columns are widely spaced enough, then you can put your openings pretty much where you like. And modern architecture often integrates the concept of pulling the building enclosure forward of the structure by maybe 200 millimeters so that you can actually have the enclosure pass right over the columns and beams. And again, that enhances that flexibility architecturally of what the facade looks like and where it has its openings. So we see this on the University of Waterloo campus as well. You can actually use pretty random locations of windows. One of the features of older buildings, which often use solid shear walls of masonry, was that you would stack the windows one above the other so that there were no offsets. And architects have explored the freedom that having framed systems allows them to by being able to say, hey, now I can put my windows and offset them and make them odd sizes and shapes, and that makes it look different. And that is one of their ideals. So the solid shear wall looks like it uses more material, because it does, but it uses lower cost material. And just as importantly, the thing that often makes the shear wall economical is that that shear wall is performing not just a superstructure function. Sometimes it's also providing partition walls between, say, residential units. Is very common in high-rise condos. Also, that shear wall is often providing the support structure for the enclosure, and so you get two functions out of that, not just a distinct superstructure only function. And here's an example of a not uncommon type of a building where there's a shear wall that is the part of the building that has either few holes or no holes, and they use that as part of the superstructure, and it also is going to be used to support the enclosure when it is built on top of this. Now, wood framing, which should be property light wood framing, that means the framing elements are relatively small and spaced relatively close together. In our current codes, close together is about 610 millimeters or less, and we routinely do it at 400 millimeters. The framing photographs I'm showing here are to show you the framing, but in most cases we are covering up that framing with sheathing. And the reason we cover it up with sheathing is so that we can get lateral bracing. So it turns that frame into something that is like a solid wall, like a solid shear wall. This is done a lot, and it allows us to build 4, 5, even 6-story wood frame buildings using standard sized wood, light wood, and standard thickness sheathing. Will get you to 3 stories. And then with a few closer spacings and a bit of engineering to pick up the higher loads, you can get to 5 and 6 stories. Now, that's light wood framing. Really, there's a very little difference structurally between a steel, hot-rolled steel with braces and a mass timber as we're seeing today. We're making the mass timber columns and beams out of glulam. They are basically being used instead of steel. We may still use steel as a diagonal brace or not. We may still use, as on the left side here, a concrete core to act as a shear wall. When we're not using the shear wall on the outside, we're using the shear wall on the inside in the form of a concrete core. Why do they do that? Well, mixed functions again. That elevator core, stairwell core, becomes not just a structural element, but has really good sound and fire resistance, which is really important for an elevator core in a residential building. Also emerging is this mix of using, say, concrete on the first floor or 2, and that first floor might have more high fire risk activities. It may also have things like car parking, which is a high fire risk activity. And then from that floor above, that first floor called a podium, we will build 3, 4, 5 floors of wood framing on top of it. So these are mixed and fulfilling needs that we have right now. If you look outside of North America, you'll find a lot of buildings that look like this, that integrate the load-bearing masonry walls with load-bearing superstructure. This mixing of 2 different systems together is really frowned upon in Canada and the United States because it's so hard to predict how it will perform. What part of this assembly takes what part of the load? How much of the lateral loads are taken by the reinforced concrete frame? How much of the lateral load is taken by the brick masonry or the concrete block masonry that fills it in? So while this is quite common to many parts of the world, it is essentially not done in North America at all anymore. So one of the benefits of these solid walls, and shear walls included, is that you can put a small opening wherever you like. It's easy to attach cladding wherever you like. And of course, you don't have to worry about separating out the movement of enclosure from wall because there is no enclosure support. It is a pure superstructure. The reason we don't do this as much anymore is that when it gets to taller buildings, this becomes quite a weighty and hence expensive solution. But just as important is that we don't want the restrictions about where we can put windows and openings and how big those windows and openings. When I say we don't want it, the architectural designers, often the owners, do not want this. And so they're saying, well, I don't want to be limited to a 2-meter wide patio door. I want the option to do much wider openings, and it depends. And the frames allow you to do that, whereas solid walls have significant constraints. And when you look at older buildings, you can see those constraints, which the designers seem to have worked around. Now, we think about this from a history point of view. In Canada and the United States, we began with masonry 300 years ago, as all serious buildings were made out of masonry. Although the first houses and first buildings that were being built in North America by the colonists were wood frame buildings, making use of what they had available. Now, for 100 years now, light wood framing has been the dominant choice in North America, and was popular as much as 200 years ago. However, around the turn of the last century, as urban areas developed, we went to high-rise buildings and higher density buildings. Steel and steel framing became a primary choice, and we had to start to figure out how to fill the voids in between the steel framing elements. Reinforced concrete became very popular after the Second World War. And again, as we moved from solid walls to frames, in the concrete case, moment frames, again, we had large openings that between the columns and the beams and the floor slabs that needed to be filled. This was what precipitated this idea that the building enclosure was separate from and is a different function than the structure that I've been talking about so far. So let's just take a quick look now at enclosure support functions. Support is just one of the functions of the building enclosure. It collects and resists those mechanical loads and transfers them to the primary structure. So again, if there is a frame, if there is a superstructure like a limited amount of shear walls, then that is what the enclosure is transferring to the floors. The floors transfer to the shear walls, or they transfer to the braced frame or the moment frame. By definition, you're not going to have gravity loads like people stomping on floors transferred through the building enclosure. That is being collected by the superstructure. It also doesn't take lateral out of plane. So think of the enclosure as a flat, say a wall or a flat roof. It's not taking the loads that are lateral and transferring them to the superstructure. The superstructure, its bracing, its moments, its shear walls are taking those and comparing them down. Now this does, again, I want to remind you that there are a significant category of building systems that combine enclosure and superstructure. One of the obvious ones is light wood framing. Load-bearing masonry in the historic past was always done this way. It is only in the modern world that the majority of larger commercial institutional buildings are separating out the enclosure support function from the building structure function. So, what are some of the systems that we use for enclosure support? In the commercial world, steel studs, light gauge steel studs, I'll describe more, are very common. CMU, or concrete masonry units, or concrete masonry, are also often used as a support structure, but confusingly, they can also be used as load-bearing. We use aluminum tubes quite distinctly in curtain wall systems, which essentially never take vertical or lateral loads. They're almost essentially always an enclosure support function only. Wood, as I mentioned, could be both its own infill support structure, or it could be part of the superstructure. It's your job to identify which it is. Cast in place concrete is almost always part of the superstructure, but it can also act as the support structure at the same time. It rarely acts only as support. And all of these systems require assembly from the outside and the inside. You build the superstructure, and then as a support structure, you have to put this together. And that limits their utility when it comes to high-rise buildings where we don't have easy access from the outside. And this has led to the development of a lot of prefabricated systems that have the entire enclosure, support and control and finish, in one product that's lifted off a truck and attached to the side of the building. Some of the original versions of that were precast concrete, but aluminum and glass curtain walls are also quite common, and steel stud systems with synthetic stucco and various other finishes have also been used widely across North America. And they are requiring that it's not just the support that we're installing, it's like the whole system is installed in a prefabricated manner, almost entirely because of the expense of access above 8 to 10 stories. Below 8 to 10 stories, there's fewer drivers and cost savings. So here's some examples. Light gauge steel, most common support structure used in North America and increasingly popular around the world. It doesn't weigh a lot, so it doesn't accumulate a lot of seismic loads. It doesn't use a lot of materials. It's quite efficient, has some environmental arguments for that. But it isn't that fire resistant. I know people think steel doesn't burn. That's true, but it gets hot and turns into spaghetti and falls apart. It's also not very moisture resistant. Yeah, sure, it doesn't rot. Instead, it corrodes. And this metal, by being efficient in materials, is only a millimeter or so thick. And so it doesn't take much corrosion to lose a tremendous amount of structural capacity. Just, what would look like surface corrosion on hot roll is sufficient to cause structural deterioration in a light gauge steel. So you see the image there was with concrete. This is an image of a steel framed system. You can see the bracing, the hot rolled red steel, the beams around the perimeter, and the infill, non-load bearing. It doesn't take any gravity loads. It doesn't take any lateral loads. What it does is it collects the wind loads out of plane and transfers them to the beam above and the beam below, or the floor above and the floor below. That's its job. It also supports the weight of the eventual enclosure finishes. So it has structural requirements, but at a very low level. Like a door has a structural requirement. So here I'm showing you some images from the Waterloo region showing concrete frame on the right, concrete frame with masonry as a shear wall. That's the concrete block on the left-hand side. And then on the opening side, where they have lots of windows and openings, they're actually installing steel studs with openings, and the shear wall you can't see is hidden behind at the corridor. So light gauge steel studs are almost always sheathed with something. That's not sheeting, it's sheathing. And in commercial construction, this has generally been made up of a non-structural, non-combustible, critical, it's non-combustible, to go with the non-combustible steel and the non-combustible fiberglass and stone wool insulation. So that has been the trend, and so to make the system moisture tolerant enough to survive construction, it had to use a special type of gypsum board, which you see here, the yellowy orange stuff. But there's now new products. In the bottom right, you see a white, there's purple, there's green. And these are all exterior gypsum products meant to be attached to steel studs to not provide any structural bracing because it's not needed. It's just a support structure. But to provide a firm surface to which you can apply finishes. And you can see the air-water barrier going on in both the left and the right, and insulation is being installed on the left and the bottom right as well. One of the key features that exhibits any enclosure support structure is that there must be movement joints between the primary structure and the actual enclosure support, because they're moving differently. If you don't have a movement joint, then the movement of the superstructure will impose loads onto the enclosure support structure and cause that enclosure support structure to buckle and fail. This is a deficiency that occurs occasionally when people forget. So the steel stud systems often use slotted holes, as you can see in the photograph, or you can use two nested C's, one on top of the other, that allows movement. And the primary responsibility for identifying how big that gap should be is the engineer of record for the structure, who says expect 19 millimeters or 3/4 inches of deflection. Okay, the person who designs the steel stud and installs it then has to accommodate that 19 millimeters of movement. So there's a bit of coordination that has to happen there. The same thing goes on with concrete masonry units. It is not that uncommon to see concrete masonry units as a infill support only. And so that means that you need to provide a movement joint between the primary structure, in this case steel, and the enclosure superstructure, support structure, which in this case is concrete masonry units. And you can see there's just a technique here for how to provide that protection of that from movement and protect against loads. Aluminum tubes is a category. It could be just light tubes or something, but really they're almost always aluminum. Occasionally we see these as being small glue lambs, but this is a pure enclosure support function. It does not take any gravity loads, does not take any lateral loads. All those loads are resisted by the building structure. And obviously I'm pointing out here that this is a pretty slick and easy way to build, but it actually is one of the more expensive ways. It's you trade off the easy for the expensive. And of course, it has very bad thermal performance. We'll find that out, is that in terms of R values, in terms of solar control, is pretty horrible. It's pretty bad for fire and sound, and pretty bad for blast resistance and flexibility. But it's shiny, and so people like it a lot. Now, there's still a need to allow movement between the superstructure and the curtain wall. In fact, this was the industry that really identified how important that was and how to manage it. Mostly you can't see the movement joints to the untrained eye because the movement is accommodated inside the aluminum tubes. The glass slides inside of a slip joint, and that allows movement. There are times, particularly in high-rise buildings or buildings with lots of lateral movement, like earthquake zones and such, where you actually have to make the frame that holds the glass quite a bit wider to accommodate the fact that you need a lot more. I mean, if you need 2 inches or 50 millimeters of movement, well, then you're going to need a bigger frame. The normal system can accommodate maybe 12 millimeters or half an inch to 3/4 inch of movement, and then you have to start going to specialty frames. Now, this is an example where the tubes in the form of windows were installed between, not outside of the superstructure, but within the superstructure. This is a hotel. There's a solid floor slab, shear walls between each of the apartment units, and it made this grid work into which they inserted this aluminum tube support structure, where they filled in some of the panels with metal and HVAC grills and some of them with glass. Terrible design idea. It seemed like a good idea at the time because it made things easy, but it ignored all kinds of performance requirements like thermal control, water control. And as you can see, maybe in this application there were too many windows given the amount of curtains that have been closed. Another thing to mention in this enclosure is that we're seeing more growth in wood infill. As I said, wood is often a superstructure and enclosure support, but we're seeing a lot more, and this started in California 30, 40 years ago, the use of, say, structural steel or even mass timber with infill or support structures made out of wood framing for both thermal, environmental, and cost reasons. So what you're seeing here in this picture is it's a fast food restaurant, and the steel frame is erected to allow for large windows. What we're looking at is going to be a large window looking into the store, but there's bunch of the back kitchen on the left hand side and so on, all can be made out of wood framing and will perform better on a number of levels, including, believe it or not, fire. Now, here's an example. Some countries are much further along in this. This is a photograph from New Zealand about 5 years ago or so. This is a relatively large office building, and it's combining a aluminum and glass curtain wall on the top. You'll see a precast concrete enclosure over top of some of the columns. And we also are seeing some opaque walls being made of that wood as a wood infill between steel superstructure. So a real mix and match that we hadn't seen in the past in North America, but we're starting to see more and more of as people look more clear-minded and rationally at what are my options? Why would I choose precast concrete? Why would I choose wood? And this is where, building science and building technology really come together, is that by understanding the reasonings behind why you would choose one system or the other, you can start having conversations with construction folks about, well, I know you don't normally do this, but hey, do you see the benefits if we were to do, say, a wood infill in a steel superstructure? And we're seeing many more of these, what would have been seen as unique or weird mixes. This is a project in Milton where we're seeing concrete shear walls, precast hollow core planks for the floors, and yet all the end walls are made of wood framing like you would build a house. And this is these combinations are being chosen for project specific, availability of trades and materials at the time, but require you to really understand the fact, what is a superstructure and its functions? What is the enclosure, and how does the support structure of the enclosure interconnect with the superstructure of the building enclosure, and how do you avoid problems to allow that to happen? So one of the key things is that if they are separate, you're going to see movement joints between the enclosure support structure and the superstructure. And so you should be able to see that. And if you can look at a building and see how the floor loads or the roof loads are carried down to the below grade condition, that will give you a good sign of what parts of the building are structure and what parts of the building are enclosure support side. Because the enclosure support is not taking the roof loads down to the grade. That's the superstructure. So I'm hoping that is both explanatory and some food for thoughts about ideas that might apply to building projects, and also so that when you're walking around looking at buildings and thinking back to projects you've been involved on, that you can start to understand what was separately a superstructure from the support structure of the enclosure. Cheers.